Hello, and this is a lecture corresponding to sections 3.1 and 3.2 from Chapter 3 of Basic Sentential Logic and Informal Fallacies for Philosophy 10 at UCSD. Um, so in these sections, what we're going to be starting off is the proof method. Now, you might ask, what is the proof method, and in particular, why are we doing the proof method to determine argument validity? We already have a method, which is the truth table method. If you have an argument, you do a truth table, and that truth table will indicate, you can tell by means of the truth table whether that argument is valid or not. So why are we spending all this time coming up with another method? Well, a couple of reasons. One is that truth tables get very, very large as the number of atomic statements involved in the argument increase. The most we dealt with on exams in Chapter 2 were 3 statements with 8 rows. But if you had 5 statements, you could have 32 rows, and that goes up exponentially with the number of atomic statements. So you could end up with having to do a truth table with 256 rows pretty quickly. Whereas the proof method, in many cases, you can demonstrate an argument is valid, even if it has a lot of atomic statements, much more easily and quickly. The second reason for doing it is it basically, for many people, proofs are just a lot more fun than truth tables. Truth tables are pretty boring. But proofs, it's almost like a puzzle or kind of like a game. There is a downside which of the proof method versus truth table, which is that if an argument is invalid, your truth table will demonstrate that right away. With a proof method, if you try to do a proof and you just can't prove that the argument is valid, you can't use the method to determine that, that doesn't mean the argument's invalid. It might just mean that you weren't clever enough to figure out how to do that proof. It might be a very difficult proof. So while you can demonstrate validity if you manage to do the proof, you can't demonstrate invalidity in the same way that you can with truth tables. But let's just stick with the that are more fun and interesting to do justification for now. So let's introduce the proof method. A couple things are going to change. First off, we're just going to change slightly how we represent an argument. So up until now, we've represented an argument this way. We've numbered the premises and the conclusion. We put a line between the premises and conclusion and put the little therefore triple dot right there also to indicate the conclusion. We're going to change this just slightly. What we're going to do is we're going to move the conclusion off to the side. So sort of align it with the last premise and it's going to move it off to the right after a slash, because we want to keep all of the space underneath the premises clear. You'll see why in a minute. And we're also going to eliminate this line. Okay, and so what we're left with is this kind of a representation of an argument. We're not numbering the conclusion anymore. We're only numbering the premises. The space underneath the premises is clear, but we're still reminding ourselves what the conclusion is by putting it off to the right after a slash. Okay, so just a slight change in how we're going to represent the arguments. Now, how does the proof method work? So here's an example. Here's an argument. The way it works is we're going to be introducing rules, inference rules and replacement rules. And what these rules do is they allow us to derive new numbered lines. So right now our only numbered lines are the premises. Premise 1 is number 1, premise 2 is number 2. Those are our only numbered lines so far. But the rules are going to allow us to write new numbered lines based on the existing ones, the ones we already have. Okay? The goal is going to be to derive a line that is the conclusion. In this case, the line is just not E. Okay? And what I'm going to do now is just kind of show you schematically how this works. So with our proof, we started off with premise 1, premise 2. Here was our conclusion. Now what I did is I wrote a new line 3. So I put a 3. I wrote the new statement corresponding to 3. And the rule simplification that I used and the line I used it on. So I used the rule simplification on line 2 to get D. Now don't worry right now about what simplification is and what it means to use a rule on a line. That's what we'll be talking about in a minute. The point is, though, that I used one of the rules on existing lines to derive a new line. Okay, so I've got a new numbered line here. I've got a number and I've got a statement, and then I have a justification, which consists of the rule I used to get this line and what prior lines I used that rule on. So I used the rule simplification on line 2 to get line 3. Okay, now I'm going to do it again. I can use, in this case, the rule of disjunctive syllogism on lines 3 and 1 to get this line. If E, then not G. And then I can use the rule of simplification on line 2 to get G. And then finally, use the rule of Modus Ponens on lines 4 and 5 to get not E. Now, notice that here, finally, I've derived a line, not E, that just is the conclusion. Okay, so that's the goal. And if you can do that, if you can use the rules to derive new lines and then eventually derive the conclusion, that shows that the argument's valid. Okay, so that's kind of how it works mechanically, practically. And you'll be doing a lot of this. In a minute, I'm going to be introducing the first couple of rules, and you'll see how they work and how you can derive new lines from them. Before I get into that, though, I want to say a little bit about why it works. Why is it that we can play this kind of puzzle game of applying rules to these lines, and if you manage to derive the conclusion here, that shows the argument is valid? Why does that work? Well, the key reason is that these rules, all of the rules you're going to get, the inference and replacement rules, they have a property that they are truth preserving. Okay, they preserve truth. And what that means is that if you apply those rules to true lines, lines that are only true, there's no false lines that you're applying them to, you're applying them to only true lines, those rules will produce only true lines. Okay? That's the key feature and that allows this method to work. Why does that work? Well, let's go back to the proof we just did. And just take my word for it, all of these rules are truth preserving, which means if we use them on a true line, it will give us a true line. Okay, so let's look at the first step of the proof. We're always going to assume our premises are true. Okay? Now, I derived line 3 by using simplification on line 2. Okay? Well, the rules are truth preserving. So if 2 is true, because that's the line I used it on, then 3 is going to be true because I got 3 by using a truth preserving rule on a true line. Right? So if 2 is true, 3 is going to be true. So now we know that 1 through 3 are all true. Well, to get line 4, I use the rule of disjunctive syllogism on 3 and 1. Well, that rule is truth preserving. They all are. So if 3 and 1 are true, line 4 is going to be true because I got 4 from 1 and 3 using truth preserving rule. And this same reasoning continues. If 1 through 4 are true, 5 is going to be true because I got 5 by a truth preserving rule that was applied to lines, you know, between 1 and 4, in this case 2, right? And finally, if 1 through 5 are all true, then 6 is going to be true, okay? And 6 is the conclusion. So what that means is, if you sort of compress this down, if the premises are true, 1 through 2, then all of the derived lines are going to be true, because you got all of the derived lines by rules that preserve truth, and you only use them on true lines. So all of your derived lines will be true if your premises are true. Okay, and the conclusion, the last one, is one of your derived lines. Okay, which means that if the premises are true, the conclusion must be true. Okay, because you derived the conclusion from the premises using truth-preserving rules. And that's the definition of validity. If the premises are true, the conclusion has to be true. So that's why the method works. Don't worry too much about why the method works. The important thing for now is just that you can do proofs. You can use them to demonstrate validity. So that's what we're going to turn to next. And this is sort of starting section 3.2. So first off, I'm going to introduce the first two inference rules that we're going to use, Modus Ponens and Modus Tollens. So the first rule, Modus Ponens, which we will abbreviate as MP. And what this rule says, this is a sort of schematic representation of the rule. And all of our rules I'm going to introduce with schematic representations. What this rule says is that if you have a conditional, and that's represented up here, phi, then psi. So you have that already on a line in your proof somewhere. And you have phi, the antecedent of that conditional. You have that somewhere on your proof. Then you can derive a new line that consists just of the consequent of that conditional. Okay? So to summarize again, this rule says that if you have a conditional on a line and you have the antecedent of that conditional on a line, then you can derive a new line that's just the consequent of that conditional. Okay, next rule, Modus Tollens. This rule says that if you have a conditional, so like Modus Ponens, it operates on a conditional, okay? But there's a difference. This one says if you have a conditional and you have the negation of the consequent, so the consequent is psi, and here I have not psi. So if I have those two things already on lines, then I can derive a new line that is just the negation of the antecedent. So the antecedent is phi, I can derive not phi. Okay, so let's see these rules in action. It'll make a lot more sense. So here's a proof. It's a very simple proof. That's only going to take one line, one step. Most of the proofs you have to do are going to take more than one step. So I have two premises. Premise 1 is a conditional. If A and B, then C. Premise 2 is a conjunction, A and B. And the conclusion is C. Now, you can derive this in one step, and here it is. I can use the rule of Modus Ponens on lines 1 and 2 to get C. And when I do that, I'm done because C is the conclusion. Now, how did I get C by using Modus Ponens on 1 and 2? Well, let me remind you of the rule of Modus Ponens. I'm going to put this rule down here. So this is Modus Ponens. It says if you have a conditional and you have the antecedent of that conditional on a line, you can infer the consequent. Well, now let's look at the proof. What this rule requires, it requires two things, a conditional and another line that's the antecedent of that conditional. And sure enough, my proof has those. Okay, to start off with, I have a conditional on line 1, and line 2 is the antecedent of that conditional. Okay, and I've kind of color-coded the correspondences here. Line 1 is my conditional. Line 2 is the antecedent. Okay, the antecedent is A and B, and sure enough, that's right here on line 2. So I've got the pieces that the rule needs, okay, for Modus Ponens. Given that I have the pieces, the rule says there's something I can do if I want to. What does it say? It says, well, if I have these two things, conditional and the antecedent, I can derive a new line that consists just of the consequent. Okay, So I can take the consequent of that conditional, boom, and make that a new line. So that's what I'm doing here. I am taking the consequent of this conditional and writing that as my new line. Okay, so because that's what the rule says I can do. Okay, now notice that the Greek statement variables, phi and psi, in the rules, the written version of the rules, they can stand for simple or compound statements. Okay, so, and we see an example of this. Phi, which is a statement variable, here it's standing for the compound statement A and B, because that's what the antecedent is. The antecedent of this conditional is A and B, so that's what phi is standing for. But it can also, these Greek variables can also stand for atomic statements, right? I use the word simple, but that's the same as atomic, sorry. Here psi stands for C. Okay, so that's why we use the statement variables. These can be either atomic or compound, doesn't matter. So hopefully that's clear. I know there's a lot of boxes and arrows here, but basically this is just indicating that 1 and 2 fit the pattern of Modus Ponens, conditional, antecedent of the conditional. That's what the rule wants to have. And if you have those, the rule says you can write a new line that's just the consequent of that conditional. Then what you have to do is not just write the new line, a number in the statement. I need to write the justification. And what the justification is it tells someone, it just records how I got line 3. And it does that by citing the rule I used, Modus Ponens, and the lines I used it on, namely the lines that correspond to what that rule requires. Okay, the antecedent, or I'm sorry, the conditional here and the antecedent. Where were those lines? Oh, they were on line 1 and 2. Okay, so this was a pretty simple proof. Let's do another proof. And there's going to be a sort of tangent I'm going to go off on in the middle of this proof to explain how negation works. So here we have a proof. There's 4 premises, and the conclusion is A if and only if K. How are we going to do that? Well, I notice I can use Modus Ponens on lines 1 and 4. So let's look at 1 and 4. I'm going to remind everyone of the rule of Modus Ponens here. So let me just go back up without all of the extra stuff. So all I'm going to do, I'm keeping all of this the same, and I'm just going to sort of throw some boxes, colored boxes, and information up here. But I'm not changing any of these statements. So the rule of Modus Ponens says, if I have a conditional and I have the negation of the consequent, I can infer the negation of the antecedent. So let's look up here. And my justification says I use Modus Ponens on 1 and 4. So I'll be able to find the conditional and the negated antecedent on lines 1 and 4. So sure, I go up here and I look at lines 1 and 4. I have a conditional, if P then not Q. And on line 4, I have the negation of the consequent. Okay, because the consequent's not Q. Line 4 is Q. Okay. Now here's the tricky thing, and this is going to be the tangent. Oh, before I get to the tangent, let me just finish my thought. So I have a conditional, negation of the consequent. Q is the negation of not Q. So the rule says I can write what on the new line? The negation of the antecedent. Phi, I can write not phi. So this is P, I wrote not P. Okay, so that's how I got line 5. Now the thing that's a little bit tricky here is you might look at the rule and say, hey, wait a minute. I thought that you had to have a conditional and then you had to have the consequent with a tilde in front of it. And that's not what's happening here. I've got a conditional, and here what I was expecting, Rick, you might say, is I was expecting not Q with a tilde in front of it. So plus one more tilde, not Q. Okay, because that would be, you might think that's how you negate not Q, is you add a tilde. Well, think of it this way. And for most people, this is intuitive, right? With this, I'll give you the short version, and a lot of people, this will just click. What this rule says is that this has to be the negation of that, right? You can get the negation of this by either adding a tilde or subtracting one. Either one of those things gives you the negation of a statement. Here I subtracted one tilde. I went from not Q to Q. Okay? So if that makes sense to you and you're happy with it, great. If you're still a little bit troubled by this, I'm going to say a few words. In the written rule, a tilde means that the statement with the tilde has to be the negation of the same statement without a tilde. Okay? So it has to be the negation, but which one has the tilde doesn't matter. What matters is that they have a different number of tildes, and that number differs by one. You can negate a statement by adding a tilde or subtracting one tilde. Either way is fine to negate a statement. So when I say this is the negation of that, well, here we added a tilde to get the negation. Here I subtracted one, but that's okay. Either of those counts as negation of. All right? You either add one or subtract one, and you've got the negation. So let's see some examples. I'm going to erase the proof we were working on for a minute. We'll get back to it in just a second, but I want to go through some examples of how this negation works. So here's another possible proof. I'm just putting it up here for illustration. You might say I want to use Modus Ponens on lines 1 and 2, and I've got a conditional. I've got the negation, not Q is the negation of Q, so I can infer the negation of the antecedent on line 3. A becomes not A. That's fine, that works, okay? What about this? If A, then not Q, Q, therefore not A, okay? Well, that's also okay, because here I have a conditional. I have the negation of the consequent. Q is the negation of not Q because it differs by one tilde. In this case, it's one less. So I'm still satisfying the rule. So I can infer the negation of the antecedent. A becomes not A. That's also fine. Okay? And that's here. I just indicated that not Q corresponds to psi. Q corresponds to not psi. Okay, because they're negation of. What about this? That's okay. This is not okay, actually, and I'll show you why. If not A, then Q. There's my conditional. Not Q. Is that the negation of this? Sure enough. Q, not Q, that differs by one tilde, so that's the negation of that. So the rule of Modus Ponens would tell me that I can infer the negation of the antecedent. Antecedent is not A. Oh, that's not the negation. That's the same thing. Not A and not A. That doesn't differ by one tilde. It's the same number of tildes, 1. So that's not good. I would have to, the rule says that I have to have the negation of the antecedent. Here I just copied the antecedent exactly as it was. I didn't negate it. So that's, I can't do that. What I would have to do in this case is take one tilde off. Or add one. Either one would be fine. So I could have if not A, then Q, not Q, that's the negation of the consequent. So I infer the negation of the antecedent. I negated it by removing one tilde, but you could also add one. I could have put not A. That also would have been the negation, and that would have been okay. Okay, so and now I'm just indicating not A becomes A, phi becomes not phi. In both cases, you've moved from a statement to its negation. That's okay. That's what the rule says. Finally, you could do this. Conditional, negation of the consequent. Q is the negation of not Q. Infer the negation of the antecedent. A is the negation of not A. That's okay also. Okay, so now let's go back to the proof. I'm done with the tangent. Let's go back to our proof. So I derived line 5 by Modus Ponens on 1 and 4. Okay, just to recap, line 1, I have a conditional. I have the negation of the consequent. Q is the negation of not Q. So the rule says I can write a new line that consists of the negation of the antecedent. Antecedent is P, so I write not P. Okay, now I'm not done, obviously. I need to derive this. But you can see one more step, I can do it, right? Because if you look at line 3, I have a conditional. 5 is the antecedent, so by modus ponens, I can get the consequent. Okay, remember modus ponens says, if you have a conditional and you have the antecedent of that conditional, okay, which I do, I have those components that I need. Conditional, what's the antecedent? Not P, do I have that? Sure enough, I've got that antecedent on a line by itself. So by modus ponens, I can derive a new line that consists just of the consequent. So that's what I put here. There's my justification, modus ponens on lines 3 and 5. And now I'm done because that is the conclusion of the proof right there. Okay? Let's do one more example. This proof also has 4 premises, and the conclusion is R. And there's only 2 rules we have. It's either modus ponens or modus tollens. So when that means that we're going to look for conditionals, and then we're either going to look for other lines that are the negation of the consequent or lines which just are the antecedent. Do we have anything that fits that pattern? Well, we got a bunch of conditionals. So now I'm going to start looking either for the antecedents, W, not S, not W, or I'm going to start looking for negations of the consequence, which would be not R, K, or S. Well, sure enough, I have one. I've got on line 2 and 4, I have the parts I need for modus tollens, right? I have conditional, I have the negation of the consequent. So by modus tollens, I can infer the negation of the antecedent. So S, not S, becomes S. That's S is the negation of not S. And again, my rule was modus tollens on lines 4 and 2. Okay, not done yet. I'm trying to get R. Okay, well now I've noticed, look, I can do modus tollens again on 3 and 5. 3 is conditional. If not W, then not S. And the consequent is not S. And I have the negation of that consequent here on line 5. Okay, so now I've got the components I need for modus tollens. Conditional, negation of consequent. So the rule says I can now write a new line that is the negation of the antecedent. Antecedent is not W, the negation of that would just be W. So I'm going to get W by modus tollens on 3 and 5. Still not done. But now look, I can do modus ponens on 1 and 6. So modus ponens, what does it require? It requires a conditional, and it requires the antecedent on a line by itself, W. Well, I've got that. I've got a conditional, and I have the antecedent. So by modus ponens, I can derive the consequent on a line by itself. The consequent is R. So I've derived R, and I use modus ponens on lines 1 and 6 to get it. And now I'm done because I finally derived the conclusion right there. Okay, that finishes up sections 3.1 and 3.2. Next up will be a continuation on chapter 3.